Hook. 00 to 020. Imagine flipping a switch and light instantly flows into your room. That instant feels like magic. But behind it is a carefully choreographed journey that stretches miles and involves giant machines, invisible forces, and constant balancing. Today, we'll trace how electricity gets from where it's made to the outlet in your house, step by step. Big picture, a simple analogy, 020 to 055. Start with a quick picture. Think of electricity like water. A power plant is the reservoir. Transmission lines are the big pipes. Substations are pumping stations that reduce pressure. And the wires on your street are the small pipes that send water into your home. That analogy helps explain the key idea. Voltage is like pressure. Higher voltage moves power more efficiently over long distances, and lower voltage is safer for your devices. 1. Where electricity is made, 055 to 140. Most electricity comes from large generators. These could be inside coal, gas, nuclear plants, giant wind turbines, or banks of solar panels feeding inverters. A generator converts mechanical motion, or sunlight, into alternating current, a flow that changes direction many times per second. The important point: generation creates the electrical energy that must immediately flow into the grid. There's very little storage on the transmission system, so production and consumption have to match closely. 2. Step up, the role of transformers in high-voltage transmission. 140 to 240. Once electricity is produced, it's fed into a transformer that raises the voltage. Why? Higher voltage means lower current for the same power, and lower current means less heat loss in the lines. So to move power hundreds of miles, operators step up voltage to hundreds of thousands of volts and send it across the transmission network. Those iconic tall towers and long cables you see between cities. Transmission lines are managed by grid operators who route power across the network like traffic controllers. They keep lines within safe limits and help reroute power when something breaks. 3. Substations and stepping down, 240 to 340. At the edge of the high-voltage system are substations. These are the highway exits of the electric grid. Substation transformers step down the voltage, from hundreds of thousands to tens of thousands, and eventually to the distribution voltages used in towns. Substations also have switches and circuit breakers to isolate faults and protect equipment. Think of substations as the neighborhood's control centers. They convert the efficient long-distance voltage into levels that local networks can handle. 4. Distribution, the last mile, 340 to 440. From substations, distribution feeders carry power along streets. These feeders operate at medium voltages and are either overhead on poles or run underground. Closer to homes, pole-mounted or pad-mounted transformers reduce voltage again, typically to a service voltage like 120-240 volts in the US, or other standard voltages elsewhere. The transformer outside your house is vital. It makes the electricity safe for household appliances. The connection from that transformer to your roof or meter is called the service drop, overhead, or service lateral, underground. 5. Meter, panel, and circuits. Electricity enters your home, 440 to 540. Your meter measures how much energy you use. After the meter, electricity goes into your circuit breaker panel. Breakers split power into circuits that supply rooms and appliances, and they protect your wiring by cutting power if there's a dangerous overload or short. Inside the house, wiring and outlets deliver power at the safe step-down voltage your devices expect. If anything goes wrong, a short circuit, a downed line, or an overloaded device, breakers and fuses are the last line of defense. 6. Keeping it balanced. Operators, frequency, and outages. 540 to 640. A key difference between electricity and many other commodities is that it's consumed the instant it's produced. Grid operators constantly balance supply and demand to keep the system stable, especially the grid's frequency, 60 Hz in the US, 50 in many other places. If generation drops or demand spikes, frequency can fall, which risks blackouts. Operators use spinning reserves, fast-responding gas turbines, batteries, and demand response to keep everything steady. Outages happen when lines fail, equipment trips, or generation is lost. The grid is designed to be resilient. Reroutes, redundancies, and protective devices help prevent single failures from becoming wide-scale blackouts. 7. New technologies changing the flow, 640 to 730. The grid used to be a one-way street, big plants to customers. Now it's becoming more flexible. Rooftop solar, home batteries, electric vehicles, and smart controls create many small sources and sinks of power. That introduces complexity, but also resilience. Microgrids can isolate and power neighborhoods during wider outages. Grid software and smart meters give operators better tools to balance and optimize flows. Safety and why you should care, 730 to 750. Understanding this journey matters because it explains safety rules. Never touch a fallen line, keep proper clearances near poles, and respect the power of even a single wire. It also explains why planned outages happen, and why utilities schedule maintenance, to protect the whole system. Concise ending and memorable takeaway, 750 to 80. Electricity is created, then its voltage is stepped up so it can travel far, then stepped down again for safe use, and the whole system must be balanced in real time. That choreography is what makes a flip of a switch feel instant. Outro, 80 to 810. If that cleared things up, subscribe to Explain Engine for more short, clear explanations about how the world really works.